Welcome back, guys. Today we're going to take a look at topic 8.3, which is applying and modeling systems of equations. So we're going to be taking a look at a wide variety of examples that relate to systems of equations. And in these examples, you're going to be required to solve either algebraically or graphically. So we're going to be using some of the skills that we've learned in the last lesson. All right, so as we work through these examples, what you're going to see is that systems of equations have a ton of real-world applications. And so each of these examples is going to show you one way that systems of equations can be applied in the real world. Taking a look at our first example, we're told that a main support cable of a suspension bridge hangs in the shape of a parabola. So that would be this shape right here. And it's modeled by the equation y equals 0.25x squared minus 10x plus 100. And we're told that x represents the number of feet from the leftmost support. So this would be our leftmost support right here. X is going to represent the distance from that support. And y represents the number of feet the cable is above the road deck for any given x value. So our height would be here, and our distance would be here. Now that's represented by x and by y. And we're told that a surveyor's line of sight is shown in the diagram. So we've got a surveyor looking up here at the suspension bridge, and these are 2 points where his line of sight crosses at that bridge. So we're first asked to write an equation for the line of sight in the form y equals mx plus b. So if you remember, when we have that formula y equals mx plus b, m represents slope and b represents our y-intercept. And we're told that the line of sight goes through the origin, which is 0, 0, and 40, 100. So we start off by writing out our equation, y equals mx plus b. Now the first thing we need to do is find our slope. So we're going to have m equals y2 minus y1 all over x2 minus x1. If it helps, you can label your coordinates, x1, y1, x2, y2. And then we can substitute in those values. So we have m equals 100 minus 0 divided by 40 minus 0. That gives us 100 divided by 40, and I'll write this as a decimal. If it's a nice decimal, we can leave it as a decimal. Sometimes we have repeating decimals, so we'd have to leave it as a fraction, but we do want our answer to be exact. Now, we have a slope of 2.5, and we're told that the line goes through the origin, meaning our b value is 0. So I have y equals 2.5x plus 0, which can just be reduced to y equals 2.5x. Now moving on to part B, we're asked to find the coordinates of the point where the line of sight first intersects the cable point P by solving the system of equations given our quadratic and given our linear equation. So we have y equals 0.25x squared minus 10x plus 100. And our second equation that we just determined is y equals 2.5x. Now, using those two equations, we're going to solve using substitution. So I'm going to take that 2.5x and I'm going to substitute it in for y. So that will give me 2.5x equals 0.25x squared minus 10x plus 100. Rearranging our equation, we want to bring everything to one side. So I'm going to subtract 2.5x from both sides. And that's going to give me 0 equals 0.25x squared minus 12.5x plus 100. Now the next thing I want to do is factor. And looking at my leading coefficient here, I have a decimal, 0.25. And so whenever we have fractions, the first thing we want to do is pull that out. So we're going to divide all of our terms by 0.25 by pulling out that GCF. So that's going to give me 0.25 x squared minus 50x plus 400. So when I take 12.5 and I divide by 0.25, I'm left with 50. Now, when I divide by 0.25 on both sides, that's going to disappear. And that leaves me with 0 equals x squared minus 50x plus 400. So I'm going to rewrite this up here. I've got x squared minus 50x plus 400 equals 0. Factoring that, I'm going to have x minus 10 times x minus 40 equals 0. That means I have x minus 10 equals 0 or x minus 40 equals 0. So x equals 10 and x equals 40. Now I can go about substituting those into my equation y equals 2.5x. So I have y equals 2.5 times 10 is going to give me y equals 25. Or I have y equals 2.5 times 40, which will give me y equals 100. So my two intersection points are going to be 10, 25 and 40, 100. Now we need to go back and check the question, see what we're being asked, and see what those numbers mean in the context of the question. So first of all, taking a look here, we're asked to find the coordinates of the point where the line of sight first intersects the cable. Well, it's going to first intersect the cable at 10, 25. So this is my answer. Let's take a look at what that means in the context of the question. So we have our line of sight here, and the origin is where this person is looking from. The first intersection point happens right here at 10, 25. Now we know 10 represents the distance from that support beam and the y value represents the height. So 10 meters from the support beam and 25 meters above the road deck is where these two are going to intersect. The other intersection point happens up here at 40, 100. But in the context of this question, we're just worried about the 10 and the 25. Let's take a look at example number 2. For this question here, I want to give you a little bit of background so you understand where our numbers are coming from or how everything relates. So engineers use something called vertical curves to improve the comfort and safety of roadways. Now these vertical curves are parabolic in shape and they're used for transitions from one straight grade to another. And each of those grade lines is tangent to the curve. Can you imagine if we were driving in the mountains and we had to go down and up and down and up and down and up? Well, instead, what happens is these curves, these vertical curves are designed so that our travel is a little bit more smooth. So there's lots of vertical curves on the Trans-Canada Highway, especially in the Rocky Mountains. And in order to construct those vertical curves, surveyors have to lay out a grid system and mark the location for the beginning of the curve and the end of the curve. Suppose surveyors model the first grade line for a section of road with a linear equation y equals negative 0.06x plus 2.6. And the second grade line is y equals 0.09x plus 2.35. And the curve is going to have the quadratic equation y equals 0.0045x squared plus 2.8. So if we take a look at our diagram up here, we've got that curve and we're going to have one line here with a negative slope. That's our first y1. And then we have a second equation here with the positive slope. Now, the first question we're asked here is to write the two systems of equations that would be used to determine the coordinates of the points of tangency. So our points of tangency are happening right here, where those points actually meet the curve. Well, our first system, we'll draw a quick sketch here. We've got our curve. We've got our two lines crossing. We're going to call this one A, and we're going to call this B. So for system A, y1 is going to be our quadratic, so we've got 0.0045x squared plus 2.8. And we have y2 being negative 0.06x plus 2.6. And then for system B, we have our parabola again. And our other linear function, which is 0.09x plus 2.35. So moving on to part B here, we're asked to use graphing technology, i.e. our graphing calculator, to show the surveyor's layout of the vertical curve, and we want to sketch that below. So taking a look at our calculator here, we're going to start by entering in our equations. So we've got 0.0045x squared plus 2.8, and then we have negative 0.06x plus 2.6. And then we have 0.09x plus 2.35. So we can graph all three equations on one graph. Now, taking a look at that graph, that doesn't give us a lot of information. So we're going to adjust our window settings, and we're going to use the window settings of -15 to 15, and we're going to go up by ones. And then we're going to go from 0 to 5 and go up by ones. Now, when you're choosing your window settings, you want to think about the context of the question. Ask yourself what numbers seem realistic in that context. Now, taking a look at that, we have our intersection points right here, and those would be our points of tangency. So we're going to just do a quick sketch. We have first our window settings. It's important to have those so that if you have to go back and work through a question, you know what settings you used. And again, these are written as x min, x max, and then x scale. And then here we have our y min, our max, and then our scale. Now, using the information from our calculator, we can sketch our parabola and our two tangent lines and make sure that we mark those points of tangency. Now, with your calculator, you can certainly get a much more detailed look at your scale, and you could adjust that scale or mark that on your graph here. All right, so the next question asks us to determine the coordinates of the points of tangency to the nearest 100th. So on our calculator, we're going to do our intersection points. So I'm going to go second calc, 5 for intersect. And because I have all three curves on here, I have to be aware of which curves I'm intersecting. So I want to intersect my parabola, so I hit enter. Now I'm intersecting it with that negative sloped line, and I hit enter. So my first intersection point is happening at -6.7, 3. And we're asked to round to the nearest 100th, so that intersection point is happening at -6.67, 3.00. And then we need to find our second intersection point. So we're going to go second calc, again, 5 for intersect. But again, now we have to be more careful with which equation we're looking at. So we want our parabola, we can hit enter. But now I don't want to intersect with the second equation. I'm going to arrow down, and that'll take me to my third equation. And then I can hit enter and enter. And that intersection point is happening at 10.00 and 3.25. Moving on, our next question asks us to interpret each point of tangency. Well, what's happening is we have our curve starting at -6.67, 3, and then our curve is ending at 10.00 and 3.25. So again, we're picturing these sections of a hill, maybe in the mountains, and they're going like this, and we want to determine where that curve's going to start. So the curve's going to start here at -6.67, 3, and it's going to move in that parabolic shape, and it's going to end at 10, 3.25, so that we have a nice smooth transition as we're driving along the highway. Now, moving on to another example, this one's going to relate to a flare. So we have a flare that's being shot up into the air, and the path of the flare is modeled by the given equation here. So we have y equals -0.096 times x minus 25 squared plus 60. And we're told that y is the height of the flare and x is the horizontal distance from where it's being shot. Now, at the same time, a telescope is placed in the same spot from where the flare was shot, and the line of sight from the telescope is modeled by the equation 8x minus 10y equals -15. And we're asked to solve the system formed by the two equations using technology, so we'll use our calculators again, and we're asked to give the answers to the nearest 10th. And then it says, explain the meaning of the solution. Sketch and label a diagram to represent your solution. So we're going to start off by graphing these in our calculator. And so for y1, we're going to have -0.096 times x minus 25 squared plus 60. For our second equation, we're going to have to rearrange that to put that into our calculator. So I'm going to take that 8x minus 10y equals -15, and I'm going to rearrange it. So I'm going to have -10y equals negative 8x minus 15. Divide by negative 10 on both sides, and I'm going to have 0.8x plus 1.5. And so my second equation will be 0.8x plus 1.5. All right, now entering these into our calculator here. Always want to make sure that you double check that your numbers are being put in correctly. And then we have 0.8x plus 1.5. Now, once again, we're going to have to adjust our window settings, and we use the context of the question to determine what realistic numbers might be. Now, taking a look here, this question or this equation here is written in vertex form. So we know that the maximum is happening at 25, 60. So if the maximum is at 60, I don't really need to go much higher than 60 for my height. And if the maximum is happening at 25, then I need to go for sure at least to 50 for my x values. We also know that we're talking about height and time, so we're not going to have values less than 0. So I'm going to set my window settings as 0 to 50, going up by 5s, and then 0 to 60, going up by 5s. And we'll take a look at what we have. So there's our flare being shot up into the air, and there's our line of sight. So off to the side here, I'm going to label my window settings. I've got 0, 50 going up by 5s, and then I have 0 and 60, and I'm also going up by 5s. And sketching a quick diagram, I have my flare being shot up and coming down, and then I have my line of sight. And I have 2 intersection points, one right here and one right here. And so we're going to take a look at what those intersection points are on our calculator. So taking a look at our intersection point, we're going to go second calc 5. And we have our second intersection point here first is 41.3 and 34.5. So we'll write that down. Rounding to the nearest tenth because that's what we're asked for in the question. And then we're going to find our initial intersection point. Now, right now my cursor's over here, and I could arrow all the way around that curve, but that would take a really long time. Instead, I'm going to trace at 0, and that's going to take me closer to the origin. And my cursor is now also closer to that intersection point. So second calc intersect, and my intersection point happens at 0.4 and 1.8. So we're going to write that one down as well. So taking a look at our situation here, we know that the x value, if we go back to the original, the x value represents the horizontal distance, and the y value represents our height. And our first intersection point here is happening at 0.4 and 1.8. And then we have one happening at 41.3 and 34.5. Now let's take a look at what those numbers mean in the context of the question. Our first intersection point here is happening at 0.4 and 1.8. So that means 0.4 feet or meters, we don't know, there actually haven't been units given in the question here, but 0.4 units from where that flare took off and 1.8 units above the ground, we're going to see that flare for the first time and it's going up. Now, as that flare is coming back down, 41.3 units and 34.5 units above the ground, we're going to see that flare come back into sight. So we have our line of sight there. We're going to see that flare 2 times, once it's going up and once it's coming down. Example 4 here, it says, after a football is kicked, it reaches a maximum height of 14 meters, and it hits the ground 32 meters from where it was kicked. After a soccer ball is kicked, it reaches a maximum height of 8 meters and it hits the ground 38 meters from where it was kicked. And we're told that the paths of both balls are parabolas, or they're parabolic in shape. And so the first thing we're asked to do is to create an equation for each of those balls. Now, in order to make that equation, we have to start off with the information that we're given. We're told that the football reaches a maximum height of 14 meters and it hits the ground 32 meters from where it was kicked. Now, while we don't know the height from which the football was kicked, we do know that it started at a distance of 0 from the point it was kicked. And so we have this football, it's been kicked. We're going to assume right now the origin until we have our equation. We don't know that for sure. But we're going to start at 0, and that ball is going to get kicked in the air and it's going to come down. And so 32 meters from where it was kicked, it's going to hit the ground. And the vertex is happening at 14 meters. The height of the vertex is happening at 14 meters. And so halfway between 0 and 32 is going to be 16. So our vertex is going to be 16, 14. So we have a vertex here at 16, 14, and we have a point at 32, 0. Because we don't know that the ball is actually being kicked from a height of 0, we cannot assume that our point is at 0, 0. So using that information and using our vertex form, y equals a times x minus p squared plus q, we can actually determine our equation. So we're going to label these as p and q and x and y, and we're going to sub into our equation. So y is 0, a is what we're looking for, and then we have 32 minus 16 squared plus 14. Simplifying that gives me a times 16 squared plus 14. Moving the 14 over, we're going to have negative 14. 16 squared is 256, so we're going to have negative 14 equals 256a. And when we divide by 256 on both sides, we're going to be left with a fraction. And so that will give us a equals negative 7 over 128. So when we reduce our fraction, we have negative 7 over 128. So that makes our final equation y equals negative 7 over 128 times x minus 16 squared plus 14. So there's the equation for the football. Moving on to our next equation, we're asked to find the path for the soccer ball. So looking back at the information that we're given, we're told that the maximum height of the soccer ball reached is 8 meters, and it hits the ground 38 meters from where it was kicked. So again, it's kicked from point 0, it lands 38 meters later, and it reaches a maximum height of 8 meters. So this one doesn't go as high up into the air. Halfway between 0 and 38 is 19. So our vertex happens at 19, 8, and our point is 38, 0. So we have 19 and 8, and our point of 38, 0. We're going to use our equation again, y equals a times x minus p squared plus q, and sub in our values. So we have y equals 0. A again is what we're looking for. 38 minus 19 squared plus 8. Simplifying, we're going to have negative 8 equals a times 19 squared. And that gives us negative 8 equals 361a. And when we divide by 361 on both sides, this will not reduce any further. So we're going to be left with a equals negative 8 over 361. It's important that you're keeping your answers exact. And so our equation for the path of the soccer ball is y equals negative 8 over 361 times x minus 19 squared plus 8. And once we have our two equations, then we can find where they intersect. So for this next question, we're asked to the nearest tenth of a meter, determine the horizontal distance that both balls have traveled when they are at the same height. So let's start off by doing a quick sketch of both paths here. So we have the first ball that comes up and down and it lands 32 meters away from where it was kicked from. And then we have another ball that's also going to come up, but it's going to land 38 meters from where it was launched. It'll have a vertex here at 19, 8. And our other one will have a vertex at 16, 14. And ultimately, we're looking for where those 2 points are intersecting, or where those 2 paths are intersecting. So graphing these on our calculator, we have negative 7 over 128. And then we have x minus 16 squared plus 14. And for our second equation, we have negative 8 over 361 times x minus 19 squared plus 8. Now with this one, our graph gives us our window settings that we need. So we're going to go to our window settings here. We need to go up to at least 38. So I'm going to go from 0 to 40, and I'll go up by 5s. And my height, I don't need to go any higher than 14, so I might go a little bit higher, maybe go from 0 to 20 and go up by 5s. And then we can graph, and the path should look very similar to what we had already sketched. All right, so we're going to intersect our graphs. And we want to make sure we round to the nearest tenth. And we have our intersection point at 27.9 and 6.24 or 6.2. So these two graphs intersect at 27.9 and 6.2. Now those are just coordinates on a graph. We need to actually interpret what those mean. Going back to our question, we're asked to determine the horizontal distance that both balls have traveled. Well, we know that x represents horizontal distance and y represents the vertical distance. So 27.9 meters from where they were kicked is where they're going to intersect. Okay, now we're going to take a look at two more examples here. Both of these are number problems. You've solved problems like this multiple times before. The only difference between what we did in grade 10 and what we're doing now is that we have some quadratics involved, but essentially we're going to build our equations and find our intersection points. So starting off with the first question here, we're told that two numbers are related. The first number, minus 12, is equal to the second number, and the square of the first number minus 30 times the second number is equal to 360. Well, I don't know about you, but sometimes when I read these problems, my head kind of starts to spin a little bit. So we're going to start off first by labeling our variables. We're talking about two numbers, and we're not told anything other than they're just two numbers. So I'm going to use x and I'm going to use y. You can use any variables that you want. I'm going to make x my first number, and I'm going to make y my second number. Sometimes we're going to be told that they're larger or smaller numbers, then I would be specific with that. But here is just first number and second number. Now I find often if I go back to the word problem, a lot of the equation is already built into the sentence. So we're told the first number minus 12. Well, the first number is x minus 12 is equal to, well, is equal to the second number, which is y. So there's my first equation. X minus 12 is equal to y. Now the next sentence, it says the square of the first number minus 30. Well, the square of the first number is x squared. Minus 30. Now it says, it doesn't just say minus 30, it says minus 30 times the second number. Well, 30 times the second number would be 30y. And then we have that is equal to 360. Sometimes instead of saying is equal to, the question might just say is. Is means equals. So we have our second equation here, x squared minus 30y equals 360. Now once we have our two equations, then we can go about solving. And in this question here, we're asked to solve algebraically. That means we have two options. We have substitution or we have elimination. That doesn't mean we can't check it with our calculator later, but if we're asked to solve algebraically, we need to use one of those two methods. And so taking a look here, I've got a linear equation and I've got a quadratic. I'm going to solve using substitution. So I'm just going to rewrite my equations down here. I've got y equals x minus 12 and x squared minus 30y equals 360. Using substitution, I'm going to sub that x minus 12 in for y. So this here is going to get subbed in right there. All right, so that gives me x squared minus 30 times x minus 12 equals 360. We're going to simplify. Remember to bring that negative through, so negative 30 times negative 12 is positive 360. And subtracting 360 from both sides, these are going to cancel out and I'll be left with 0. So that gives me x squared minus 30x equals 0. Factoring, I have x times x minus 30 equals 0. So that means I have two values of x. I have x equals 0 and I have x equals 30. So I'm going to have to substitute both of them back in. I've already subbed into the second equation, so now I'm going to sub into my first equation. So the first one I'm going to have is y equals 0 minus 12, which is going to give me negative 12. And for the second one, I'm going to have y equals 30 minus 12, which is 18. So my pairs of numbers are either going to be 0 and -12, or I could say and, because they both work, 30, 18. So again, I have two solutions. Now, sometimes I might have two solutions, but when I go back and look at the question, there might be other restrictions, like it's a natural number or an integer, and then I might end up eliminating one of these, even if it does work in the system. Now we're going to move on to our final example. And in this one here, we are specifically told that our numbers are integers. So it says determine two integers such that the sum of the smaller number and twice the larger number is 46. Head spinning already? Yeah, mine too. Also, when the square of the smaller number is decreased by 3 times the larger, the result is 93. Again, lots of information thrown at you. Let's start off by labeling our variables. We're told in the question that we're dealing with integers. So integers means that there are no decimals, but we can have negative numbers. But the first thing I think is no decimals allowed. Okay. And we can have positive or negative numbers. Now we're told that the sum of the smaller number and twice the larger number. So we're dealing with a smaller number and a larger number. So I'm going to make x my smaller number, and I'm going to make y my larger number. Now you can certainly use other variables again. You can use a and b, or you could use s and l if that would help. Now I'm going to go back to the problem and see if I can use the sentence to build my equation. So the sum of the smaller number and twice the larger number. Well, the smaller number is x. We're talking about sum. Sum means add. So x plus twice the larger is 2y, so equals 46. So my first equation is going to be x plus 2y equals 46. Now my second equation, it says when the square of the smaller number is decreased. So the square of the smaller number, that's x squared, is decreased by. So that means something is being subtracted from the x squared. So that means x squared minus 3 times the larger. Well, the larger is y, so 3 times y. The result is, in other words, equals 93. So my second equation will be x squared minus 3y equals 93. Again, we're being asked to algebraically solve the system of equations. So taking a look here, this one might set up really nicely using elimination. And in order to solve using elimination, I need to get rid of my y values. And so I have a 2y and a 3y, so I'm going to multiply this first equation here by 3 because my lowest common multiple is 6. And I'm going to multiply the second equation by 2. So that's going to give me 3x plus 6y equals 46 times 3, which is 138. Always remember to multiply that 3 all the way through. We don't want to forget about the 46. And then the next one I have here, 2x squared minus 6y equals 186. Now these are opposite signs, so I'm going to add my equations together. 3x plus 2x squared, well, those aren't like terms, so that's just going to leave me with 2x squared plus 3x. Negative 6y and a positive 6y are going to cancel out. And I have 138 plus 186, which is 324. So now I have 2x squared plus 3x. I'm going to bring over the 324 equals 0. Now once I have my equation, my next step is to factor. Now this one's a little bit trickier. I know that for 2, my factors are 1 and 2. There's not a lot of choice, but 324 has a lot of factors to work with. So I'm just going to list them all out here quickly. And once I have my factors listed, I want to try to find a combination that's going to get me to 3. Well, the one that's going to get me there is 12 and 27. All right, so here I'm going to set up my chart. I'm going to have 2x and x. I want the 2 to go with the 12. I want the x to go with the 27. I'm just going to check that that works. 2x times 12 is 24x. X times 27 is 27x. I want a positive 3, and because this is a negative product, that means I have opposite signs. So positive 3 means my 27 will be positive and my 24 will be negative. So that gives me my factors of 2x plus 27 and x minus 12. So now I have 2x plus 27 and x minus 12 equals 0. And solving, that means x equals negative 27 over 2 and x equals 12. But wait a minute, we were told that our numbers are integers. So that means we're going to eliminate this one as an option, and we just have x equals 12. So we don't need to substitute them both back in because this one already is not an integer. So we're going to take that x equals 12 and we're going to sub it back into either equation. I've chosen to sub it into the first equation here. So I have x plus 2y equals 46. And that's going to give me 12 plus 2y equals 46. 46 minus 12 gives me 34. So I have 2y equals 34. Divide by 2 on both sides, and we're going to have y equals 17. So my numbers are going to be 12 and 17. And once again, we didn't have to worry about the other number because it was not an integer. Well, there you have it. There are 6 different examples of ways that we can use systems of equations. Hopefully you've got enough of a variety there to work with, especially when you're working with those questions in context. Make sure you pay attention to what your variables represent and use the information in the word problems to set up your window settings when you're having to solve graphically. Hopefully this has given you enough to work with. Have a great day, and we'll see you soon.